course, but I've had all the midterms for my Fairfield subjects this week, so I've been run off my feet. I should coordinate my work better. Anyway, okay, I think that's good. Yeah, that looks good. So here we are again, CET466 Logic Design. We don't have much more to go over, right? I think what I want to do from here on in is spend more time on projects, on labs. We may need to go back over some things. I do want to try and one of the lab groups has an issue with the USB driver not working, so they can't program the board. So I would like to try and resolve that somehow. If that means splitting the group up, we'll do that. But I'd like to see if there's if the community, the CET466 community, has any suggestions about problems with USB drivers. Actually, can I? I know, Stephen, you've had an issue. Has anybody else had an issue who has one of the boards? Has anybody else had a problem programming the board? Let me just go to the discussion channel. Okay, I'm going to take that as a no, not hearing any issues. So yeah, we'll see. I'll see what we can do to facilitate getting things to happen. So let's just let's just continue on with the slides. Right, so instead of doing the 10 labs that I had sort of planned, I've backed off that, so we'll try and get through 8 setup labs, and I think I've seen some submissions for lab 5. I keep getting lots of bloodly bloops and I'm not quite sure why that's coming across. I'm just going to quit out of some of my other messaging stuff and see if that stops all the noise. Okay, so last week, so 2 weeks ago, we talked about attributes and with select statements. Last time we talked about VHDL delay modeling and data types. And one thing that I was hopeful of is that you may have taken this part, the VHDL data types, as a hint for, I'm going to have to go back to, I think it's lab 6, right? As a hint for lab 6. So let me make it explicit. The approach we took to lab 6 was the discrete logic approach to lab 6, right? We decided we were doing a design. We decided that was going to use the full adder and 4 instances of the full adder, and then connecting it up. Well, let's just scroll down to right, where's there. So we decided that this was going to be our approach to making a 4-bit adder in VHDL. And that's the problem. It's not the look ahead, although that is a problem. It's not that we can necessarily fix the problem by using that look ahead idea. It's that because there's still going to be a bit of a problem unless you really do some extraordinary things with this approach. So my suggestion is that you look for another approach for Lab 6 to deal with wherever the glitch picture got to, right? These are they're a bit hard to see, but there's glitches here, there's glitches here, there's a lot of glitches there, right? And it's primarily because of delay paths through the logic, the way we set up the logic. And the problem is we are not using the power that we have with VHDL, right? The reason why this VHDL data types is going to help is because we have things like integers. It's because we have operations like a plus sign in VHDL. Remember, the logical OR operation is written as OR. This character in VHDL means addition. Okay? So what you can do is you can actually run, you can take away all of that scaffolding that we put in place for the full 4-bit adder, and just think about adding 2 4-bit numbers. Right? We don't have to do this when we're talking VHDL. And let me just see if I can. Right, so my implementation of the 4-bit adder now looks like that. Right, I'm just using addition between 3 things. I've got A in, B in, and the subtract bit. And I'm using the VHDL concatenation operator, the ampersand, to add a single digit 0 to the front of A in, because A in, let's check, A in is a stated logic vector so it's a 4-bit input. Same with B in. And then I've defined a constant which is just a single 0, and I've defined a constant which is is 4 zeros, 4 down to 1 instead of 4 down to 0, so that I can then add, this ends up now being 3 5-bit numbers, and then I can take the lower order 4 bits, and that's my sum, and I can take the most significant bit, and that's my carry output. Now, what I haven't done in this implementation is I haven't done the negation, right? We had a, and I think we called it in our original implementation, we called that subtract, right? And I haven't done that here. What that input does is it does the 2's complement. Of the B input in this case. And again, just because that's what this way of doing it doesn't mean we have to do the same thing in our VHDL implementation. Right, so I haven't shown you how to do that, make it an adder subtractor. I've only shown you how to make it an adder. But I think you should be able to figure out how to make it an adder subtractor reasonably easily. Any questions about that? So I do want to spend a lot more time today on labs, but I do want to show you one other thing about Quartus, and that is, and I didn't have the time to put together any appropriate notes, so I've done what any of us would do. I've gone onto the internet and I've found some notes, and I can show you how it works live on Quartus. But let's just quickly have a look at the notes. Right, so actually, before we go there, what do I want to see? I want to see this. Right, so this is the GitHub repository for this course, and there's a picture of the board. There's an annotated picture of the board. There's all the pinouts. And one thing you should be aware of is that there are schematics available for the board, right? And they're the schematics that I've been doling these out piece by piece. So this particular link, I'll put this in the Discord links channel. So okay, so that should take you directly there. Unfortunately, I can't show this in any detail without downloading the PDF, and then I can zoom a bit better. Right, so the pieces that I've shown you before, wherever they got to, are the dip switch and the LEDs. And what was the other one? The other one was the, is it up here? Anyway, the one I wanted to show you now, and it's a bit hard to see. Let's see if we can really No, it's not letting me zoom in any further, but we probably can't read on the stream, but what this is saying is that the clock frequency for the board is 50 megahertz, right? And that, if we go back to here, right, this clock frequency on pin 23 is where you get that 50 megahertz from. Now the problem with 50 megahertz is it's probably not the clock frequency we want to use, right? So I know, let's go here, right? I know one way to deal with that is to, let me just go back there and go back there. Right, one way to deal with that is to oh, we got it there already. That's the one. Okay, so one way to deal with that is, instead of using the FPGA clock, right, what we can do is we can just connect up one of these switches, right? And in our pin planner, we can connect key 1, whatever it is, as the clock for our input, right, for our entity. Now can anybody, except for Yasmin and her group, who already know the answer to this, can anybody tell me why that could be a problem? Okay, I'm going to go with bingo, and I'll call people out. Haha. I know the answer to this. I'm not going to... I should excuse myself from... And Yasmin, no! I know you know the answer. Okay.
Are you typing this?
Probably. I've got it. I'm putting it in the wrong. I put in the links. Let me clear those. So the next person who came up was Javier. So Javier, can you tell me what the problem is?
Could it be that like it won't recognize the transition state? That it just is on or off, or could it just be the fact that it's active low?
Active low doesn't matter. You can have an active low clock. That's okay. Okay, let me see if somebody else, and I'll do it in the discussion. Stephen, any suggestions? I keep getting blue loop. Not quite sure what the...
Is your Discord on streamer mode?
Probably. Does that mean it's losing...
Streamer mode will disenable the sound effect in Discord. If you don't have it on, then you just get a bunch of notifications when someone sends you a message or when they pop in and out of the voice chat.
Okay. Not quite sure what it is then. String quality. This is probably okay. 30 frames a second, 720p. No, Stephen? Nothing? No thoughts? Let's try again. Kyle Bechtold. Any thoughts? Not sure? That's okay. We'll see if we can get through everybody. Abraham, how about you? Any thoughts? Oh, and my system restarted, and I forgot to update to the latest version of the. Okay, thanks, Abraham. The latest version of the bot, which actually uses your nicknames rather than Ray. Any ideas? Why me? Because the bot said so, and we all do what bots say.
So could you repeat the question again?
So the issue is sometimes we need a clock on our VHDL, right? And the problem
Right.
is that the board has one clock and it's running at 50 megahertz. So one solution that some people have come up with is to just use one of the push button switches on the board as the clock. That way they can make it, you can't have it running at, I don't know, 100 hertz, that you'd have to go really, really quickly.
Right.
But you can clock things just by pressing the push button and letting it go. Yeah, not sure? Okay. Well, so the issue is, well, let's see if I can go back to the. Right, the issue is a lot of the. Where did I see it? Right. On the buzzer, you've got effectively a switch, right? That's a transistor, and I'm seeing if there's another one here somewhere. But basically, you've got there we go. So you've got transistors that will act as switches. However, what's different about between a transistor and this switch is that switch is mechanical, right? And the trouble with a mechanical switch is that when you go from say closed to open, right? So if we connected that up to plus 5 volts, and we initially had the switch closed like that, and then we moved it to open, what we would see here is not 5 volts drop 0 volts. What we would see instead is something more like that, where you've got this bounce on the mechanical switch, because it doesn't cleanly break and cleanly close. On the other end, once you close it, right, if you go the other way and you close it, it doesn't just go straight up. It chatters, it bounces. And because of that, instead of just getting a single transition, you might get 2, 3, 4, lots of transitions every time you press the button, right? And so the problem is in using a switch to do this is mechanical bounce. So you get, and what that means is you get more than one clock cycle if you're using it as a clock per button press. So if you're looking for just being able to see the change one at a time, one clock transition at a time, then that's not going to work very well. Okay.
Right.
So what I thought I'd do now is see how we can deal with that, right? So what I've done here is a simple device that aims to, or a simple device that aims to do division. And I'm not sure I got the, oh, I put it there. Right, so so here's an entity. It's got a clock input and it's got a single output. And what I'm going to do is I'm going to put a process together that on a positive going clock transition, it's going to change the output, which I'm going to call divided clock, right? I'm setting our output variable to be equal to our signal divided clock. And what divided clock does is every time the count, right, and a count is an integer value, every time the count hits, in this case, this is 5 million, right, every time the count hits 5 million, it's going to reset the count and it's going to change the divided clock value to whatever it wasn't, right? So it flip-flops between 0 and 1, which is usually what you want a clock to do. And I'm a little worried now because even though I was happy to see the LED flashing, based on the fact that the schematics are telling me the clock signal is a 50 megahertz clock, and based on the fact that I'm dividing by oh, I see what's happening. It's going faster than it should. Oh, maybe. Oh no, it should be right. We should be protected with that. Basically, let me see if I can. I don't know whether I can. How can I do this? I should have thought of this before. Let me see if I can plug. I don't have enough. Don't have enough, or do I have enough? See if that plugs in there. That plugs in there. I'm just trying to figure out how to show you. Let me see if I can grab that. And I might have to reset it once it's back. Right, so let's see if I can see Discord. Yeah, this is not really the best, is it? I've got too much stuff happening. Let me swap to that one. That might be slightly bigger. And what am I looking at? Yeah, that's it's not going to work, is it? I've got for the green screen setup, I've got rather bizarre settings on my webcam. Let me just see if I can take the transform off there. Oh, it's a filter. Yeah, let me not do that. I will probably screw it up if I try and do it live online. So let's just put that back to mostly where it is. So basically what I'm trying to show you, and I don't think I can, because if I move it over it's going to pull everything, is the LED is flashing at about 5... Oh, maybe it's alright. I was thinking it should be flashing at 10 times a second, but maybe it should only be flashing at 5 times a second. What I'm going to do though is I'm going to see if I can... no, it's probably alright. I'm doing the math wrong. What it should do now, I've just changed the... let me go back to mini-me. That way you can actually see what's there. Right, what I did then is I changed that clock division number from 5 million to 50 million. So now what should happen is I should be able to I should see the clock, the LED go on for 1 second and off for 1 second, right? My confusion was I thought the LED should be flashing 10 times a second, but it should only be flashing 5 times a second. It should be changing state 10 times a second. But let me just program that and see what it looks like. And now it's doing that. Okay, so it is all good. I wish I might take a break at some point and see if I can rig up another camera on another computer so I can show you the board properly. That would be good. Okay, so this is one way we could do a clock divider, right? Does everybody understand what's happening on that? I don't know whether I hope you can see it in big enough font. Let me maybe just make the see if I can change the properties. Was it? I forgot. Fonts. No, that one it didn't change. Let's detach the window. There we go. That might be bigger. Text editor, fonts. There we go. Okay, that might be a little easier to read, maybe. Okay, so what's happening here is, as I said, we've got a clock in and we've got a single output, and I have two variables. I have a counter, which is an integer, and I have a divided clock, which is eventually going to be my output. And outside of the process statement, I wire that up, right? Remember, outside of a process statement, everything happens all the time, right? So this is effectively just taking my signal, my internal signal divided clock, and wiring it straight to the output. And then my process statement has a sensitivity list that will look at everything in the sensitivity list and execute the process if anything in the sensitivity list changes. So if the clock changes, it'll do it. If the count changes, it'll do it. If the divided clock changes, it'll do it. So then within the process statement, we check that we have a positive going transition. Remember, clock event means that there was a change in clock, and clock equals 1 means that we're doing a positive going transition. and then we check to see if the count is 50 million. If it is, then we reset the count to 0 and we toggle the clock, or toggle divided clock. If count is not equal to 50 million, then we add 1 to the count, and I decided to so I've done a few things here that may look a little bit nonsensical, and the reason I've done it is because I was getting warnings in my compilation. Let me just show you what I mean. Right? One nonsensical thing is just doing that, right? Divided clock goes to divided clock. That doesn't appear to actually do anything. And the other nonsensical thing possibly is to execute this process if count or divided clock change. Let me show you what happens if I comment that out, and if I change the process statement to not include count and divided clock in the sensitivity list. Okay, so there's that. And let me do a recompile. And the first warning is not something we can do much about because we don't have the appropriate version of the software. Oh, and this time around it hasn't given me the same warnings. That is, of course, let me just that is good. Let me just clean the project, and we'll go with all revisions, and we'll see if it does the same thing. It might be because of other changes I've made that the warnings. So the two warnings that I got, one of them was it was complaining that count and divided clock were being read in the process, and but were not part of the sensitivity list. So I put them in the sensitivity list to remove the warning. The other one it had was that, and I think I know why that one was set up. I originally had, where's it gone? Right, I originally had, I didn't have this protection around the other if statement, and I suspect that was what is now removing the warning. Okay, so let me just see, now that that's compiled, let me just see that does the appropriate thing still. And yes, it's doing the appropriate thing still. So the other thing I should show you is, so does everybody understand what I'm doing in this code? All right, let me just, wherever Discord got to, there it is. Right, so the aim is to And let me put that down here. The aim is to allow right, the aim is to allow us to slow down the clock. And that's what's happening here. So we've got our process, and the only thing it's now changing on is the clock, and then we've got a protection here that says we want a rising edge of the clock. Then every time the count reaches 50 million, we toggle the internal signal called divided clock, and otherwise we just increase the counter. So what that should do is, if our clock is coming in at a rate, and I'm not going to be able to do a difference of 50 million, but the output is going to be much slower. Okay, and I might just take maybe a 5-minute break and see if I can set up another camera to show you what's happening. I might have to do a bit of rejigging. Before we do that, does anybody have any questions? Is that am I making sense? Let me
What you're saying is clear.
yeah, it's okay. Okay, so let's just have a quick break. And like I said, yeah, ice cream would be good right now. I'll see if I can set up the camera on the other computer, and see if I can connect up to Discord via the other computer. But yeah, I should have thought of that before. Sorry about this. Let me just pull that up, and I'll put a timer on for let's make it 10 minutes, and I'll come back, and hopefully I'll be able to show you things in a little bit more clarity, so I can show you the board. Now, how do we do this? I'm still playing a little bit. I've got the... there we go. That might be a bit better. There, okay. So just give me a minute. I'll be back shortly. Okay, let's get rid of that. Let's go here. Yeah, I'll go with coffee too, Harvey. I think that I should be able to just do that. Here we go. Right, so I don't like the aspect ratio, but that's the board, and you can see the LED there blinking on for a second and then off for a second. Okay, so that should be okay. Let me you can see some of my peace lilies there. Let's just go through that again. So I hope the division there is okay. I think I got a... Did I forget to do that? I forgot to do that. Let me put that back on. So I'm back as mini-me. So that code up there, I've got to get my finger pointing in the right direction. That should divide the clock by 50 million. So it should go from 50 megahertz to... Well, that's actually going to be I think it's going to be a half a hertz clock, right? Because it's got a period of two seconds. It's going to be on for a second and then off for a second, on for a second and then off for a second. Then what I've done is I've used the pin planner, right, to connect the clock up to pin 23, and let's go back here, right? Remember our FPGA clock is pin 23, and I've forgotten what number. Yeah, pin 87 is LED 1, and that's why that LED is the one that's blinking, because I set up the pin planner to connect the input to my VHDL device to the onboard clock, and the output of my VHDL device to pin 87. Okay. So that's all well and good, but there's other ways to do the same thing or a similar thing. And one thing we haven't looked at, don't need that anymore, and let's just see if we can get that back to a reasonable aspect ratio. Yeah, it decides to right. One thing we can do is and that we haven't looked at all before is there are library functions available within quarters, right? In particular, there's various sorts of math functions, and even more particular, there's a thing called a counter. Okay, so what I'm going to do is I'm going to close this project, and I'm going to create a new project. Right, and I'm going to try and do, this is lecture 9 still, but this project is going to be called using LPM counter. Yeah, let's select it. Let's call it part 2. And we're just going to create an empty project. I don't have any files to add, so I'm just going to say next. I'm going to figure out what the where the C8 version is, which is the one we're using. Right. I'm going to select Model Sim Altera and VHDL for our simulation version, and that should be setting it up. Okay, so where was that again? It was under arithmetic. And what I'm going to do is I'm going to do things a little differently. I'm going to do it using the block diagram. Okay, and I'm going to use the I don't want to do that, sorry. I have forgotten how to create the instance. There we go. So what I've done Right, I'm using the schematic approach now, this BDF approach, and I'm going to go insert symbol, and then this IP catalog is available. Looks slightly different, but it's basically the same stuff. And what we should be able to find is the LPM counter. Okay, and we can add that there. So this is quite a complicated beast. And what we should be able to do, and I've forgotten how to do it again. Apologies for this. Oh, I see. Let's try that again. What I should have done is, so we want there. Ooh. It should give me the project, the setup wizard, but it seems to have. That's the problem with having taught this class previously on version 14 of Quartus. This is version 20, so they've changed a few things. What I'm looking for is the I want to be able to insert one of those devices, and it should give me the option here for launching the wizard to set up the parameters on that device. Let me just do a bit of Googling. I apologize for this. Hmm. It doesn't seem to be the right one either. Anyway, let's just do the insert and see what happens. See if we can force it to come up with the configuration. See, what I want to be able to do is insert yeah. What should happen is I should be able to configure this device, right? This library has all sorts of things that we can do, all sorts of functions that we can do, and this particular one is an up-down counter, right? And it's got various parameters, as you can see, all of the pins and everything there. But what I really want to be able to do is I want to try and do exactly what I did directly in VHDL, but using this device. And I should be able to do that if I could figure out how to get the configuration wizard to start up. Because at the moment it's I thought I had it starting up yesterday, and I don't know why it's not doing it now. Okay, so that's all the code for it, which we don't want to actually see. Yeah, I think I'm going to have to let's do it. Yeah, I apologize. This is that brought it up. Okay. Sorry about that. So I thought I could do it with the other way around, but apparently not. So this is the configuration wizard for this particular counter, right? And the first thing it's asking is how, and I don't know whether I can change the size of this so you can actually see it. Doesn't look like it's configurable. But what it's asking is how wide should the output bus, right? Here's the device, and let me just take that, and I'll dump that in the discussion channel. So that maybe you can see it there. Okay, so what you've got is you've got the clock on one side, and you've got the output, the counter information on the other side. And the first question it's asking is how many bits do you need in the output? and at the moment the default is 8 bits, but you can see it goes all the way up to 256 bits of output. Okay, so let's think about what we want to output, right? We want to output right, 50, oops, that's 20, 50, 1, 2, 3, 1, 2, 3. We want to output 50 million. So how many bits does that mean we need? We need log of 50 million divided by log of 2, and the number we get is 25.57. So in order to get all the way up to 50 million, we need at least 26 bits. Okay, so we need to go down here and select 26 bits. This particular device, we can make it go up or down or have an up-down input. We don't care about this, we just want it to count up and then reset to 0, so we're just going to keep it as the up only option. Right, and what sort of counter? Do we want plain binary? No, we don't want plain binary, we want a modulus, and we want that modulus to be 50 million. We don't want any other, let me just take that picture as well. Right, we don't want any other maybe, there it goes. We don't want any other any clock enable or carry in or carry out or any of that sort of stuff. So we could just do that. Then the next page, do we want any optional inputs? We don't want any of those either, so I'm just going to leave them at their default values. And next, and to properly simulate the generated design files, the following simulation file is needed, LPM. So let's just do that. Okay, so that's good. And one thing you'll notice down the bottom left here is it's talking about resource usage, and it's saying that we need 26 lookup tables and 26 registers. So it might be interesting to, and this is it looks like it only has the VHDL, sorry, the Verilog version. So that may not necessarily be quite what we want. And I'm going to select all of the pieces that we want there. So yeah, and I'm going to say I want to automatically add those files to the so let's just see what files they are. Right, so we've got a QIP file, and it unfortunately it's generated a Verilog file. which may be not quite what we want. Right, so there's the my counter verilog file, and that's taking me straight into the wizard again. Okay, I am not doing a good job of this morning. I apologize. Too much other stuff happening. But anyway, the idea is that that counter is now a 26-bit counter, and it is a modulo 50 million counter. The input is a clock. The output is the 26 bits of the counter, and we probably only want to access the most significant bit if we're going to do the same thing as our the VHDL that I showed you before. Okay. I'm gonna leave it there. I really should have prepared that a little bit better. But there's another way to do something similar, and that is to use a maybe I should have, that's where the selection was. There's another way to do something similar, and that is to use a PLL, a phase lock loop. Okay, and this one, you've got to first of all tell it what the input frequency is, and it's going to be different for different boards. But we know for this board the input frequency is 50 megahertz. And then we can go here, go with, let me just take those screenshots again so we've got them. Right, so this is the phase lock loop, and I've changed that, what is the frequency of the in clock 0 input, from 100, which is what its default was, to 50 megahertz, which is what our board uses. And then on the next screen, I'm not going to change anything from the default values. And nor on the next screen am I going to change anything from the default values. Nor the next one. I do have to change the defaults soon. I just haven't reached this. This one is just has a bit more configuration available than the counter. And we don't want that to change, so we're just going to do the, again, it's gone on to step 2 or page 2, but it's still going to, I'm still just going to use the default values. Okay. So now what we can do, as you can see, maybe if I give you a screenshot, it might be easier to show you. now what we've got is we can configure, given the input clock, which we said was 50 megahertz, now what this mega function lets you do is it allows you to set up to 5 different other clocks, right? And you can see it goes from clock C0 over here to clock C4. And there's various ways to set it up. One way is to get it to try and do it yourself, and it's to right. Rather than 100 megahertz, I'm going to say it's going to be 1 megahertz. Right, that's the way to do that. If I wanted to do what we did in the VHDL and go from 50 megahertz to 1, or I suppose it's 0.5 hertz, what I'd have to do is do something like this. That's going to be wrong. It's going to be 02 perhaps. Right, now the problem is the way a PLL works. Actually, does anybody know what a PLL is? Let me go with bingo. Bray, do you know what
Well, got me again.
Yeah, got you again.
Ooh. There's nothing that Google can't tell me.
There is nothing that Google can't tell you, but you've got to be quick with your searching.
Yeah, you're right.
Okay. So let me. I'm not.
Phase lock loop. Is that what it is?
It is a phase lock loop. That's correct. Right. So let me figure out where that got to. So the first, this approach up here, right, the one that we did by hand, and the LPM counter approach just basically did the same thing, right? We for every 0 up to, well, say 49 million, right? 99999. We just did that. We just did that count, and every time we hit the boundary, then we make a change one way or the other, right? A phase lock loop does things. So phase locked loop, or PLL, does things a bit differently. What it does is it takes a clock input just like the other one, right? And then it does a, depending on which way you look at it, a comparison, and that generates an error, and we do something with the error and output the and from that output we feed it back. In fact, there's probably another box here. Okay, and the aim is that the reason for the name is there is a lock or a synchronization between what's happening on the input and what's happening on the output. In this case, the ratio may only be 2 to 1. But it's doing something very different from our counter approach, right? And I've forgotten which way round it is. I think this might be a divider and this might be a multiplier. But basically, the relationship between the frequency of the output clock and the frequency of the input clock is a rational number, right? The numerator divided by the denominator. And I think you can see here that this, so I'm using the top line of that that screenshot where it says enter output clock frequency, and what that does is it tries to match. It tries to do get the output clock frequency that I'm asking for given the 50 megahertz input clock. Unfortunately, the only options for the frequency value is megahertz, so I have to do something silly like that. So let's just see what that is. I probably should make that. Right, so that's 0.2. So I probably don't want 0.2 hertz. I probably want that one. Now, what it's trying to do is it's trying to figure out that N and that D so that I get the relationship between 50 megahertz and the other, right? So, but as you can see up here, there's, maybe you can't read it. I don't think I gave you the one with the error. Let me just send you the one with the error. What it's saying is it can't make that, it can't choose an N and a D, a numerator and a denominator, to make that frequency that we're asking for. Okay, so it can't go straight from a 50 megahertz clock down to a 1 hertz clock or a 0.05 hertz clock. Okay, but let's just say it goes. Let's just say that we want to make the output frequency 1 megahertz. If we make the output frequency 1 megahertz, then it chooses the division factor to be 50 and the multiplication factor to be 1. And what I think you saw on the previous one is the maximum division factor is only 256. Okay. So we can do that one, right? We can go from 50. We can go from 50 megahertz down to 1 megahertz. Let's see how low we can make it go. Right, looks like we can go to what's that? That's going to be 5 kilohertz. We can go to 2 kilohertz. we can go to 1500 hertz. Let's see if we can go to 1200 hertz. We can. We can go to 1100. We can't go to 1100 hertz. We can go to 1200 hertz. 1150? No, it looks like about 1200 is the lowest we can go. So you should be able to see that the division factor on this new one, and again I'm putting the screenshot in the discussion links, is 125,000, and then the multiplication factor is 3. Okay, so what it lets you do, what a phase lock loop lets you do, is take an input clock frequency and form a clock of another frequency that is rationally related to the original frequency. Okay, so that numerator and denominator lets you make the relationship. So this one we're going to get down to what did I say? That's 1.2 kilohertz. And we could set up another clock, right, to do it. I was wondering, whether I could then take the output of C0 and put it into C1, so we could maybe chain phase lock loops together, but I can't see how I do that with this one. Okay, so again, I'm apologising too much, but I apologise again for the disorganised approach to this today. The key thing I wanted you to take away from it is that if you need a clock that's different from the one that the board gives you, there are different ways to fix that. One way is to do it by yourself. And there are 2 other ways to do it using library functions in within Quartus. And as you can see, there's lots of interesting things happening. Right, we've got I/O. We've got bridges and adapters. We've got clocks and resets. We've got configuration and programming, right? Maybe that'd be interesting for some. I'm not sure what's under audio and video. Right, we've got a 16:2 character display. We've got audio and video configuration. And there's a USB controller, right? We could figure out how to use our FPGA to drive a USB port, or there is actually a PS2 port on this board as well. We could write a PS2 controller. That was the old way you'd connect your computer up to a keyboard or a mouse through the PS2 connector. Okay, I'm pretty much out of stuff I want to really get to you. The main thing I wanted you to get out of today is the fact that there is a library, and I meant to say here, right? Let me write it now. The main thing I wanted you to get out of today is there is a library of functions. Right, and I looked at two of them. I looked at the counter, and I looked at the PLL, the phase lock loop. Okay, let's see if anybody has any questions. Is that okay? Okay.
I had a question about how do you, I don't know if you can or if it's even worth it, but is there a way to add the function that you implemented from the library to the VHDL?
Yeah, I think I saw that, right? So I think when I was going a little bit too quickly. Let me just go back to the arithmetic, right, and the counter which was generating it in right. I forgot to select VHDL when I double clicked on the library function. So when it generated it, it generated the Verilog version, right? So if I had seen what I was doing and not tried to do it too quickly, I would have noticed that I should have clicked on the give me the VHDL type, and then that should generate the oh, that's a multiplier. Sorry, we wanted the counter, didn't we? Right.
Would that be considered like a component? Would you implement that into the VHDL code as a component, like an already made?
That's correct. So what you can do is you can set this up, and let's just set it up the way we were supposed to, 26 bits, and we wanted a modulus of 50 million. I can't count. That's 500,000. That's 5 million. That's 50 million, I think. Let's just count the zeros. Even the font is a bit small for me, and I'm sitting right next to it. Okay. And then we don't want anything else. And I'm going to... Right, so now it's going to generate the instantiation template, and that's the way you would use the device. Okay?
Okay, thanks.
Yeah, you're welcome. And let's just see if we can open up that VHDL counter. There's the instantiation one. I think that's the one we want. Right, so that's the way we would instantiate the counter. We'd have to cut and paste that. Let's see if I can open up. I don't know whether it'll let me open that up without pulling up the wizard. Yeah, it pulls up the wizard. Okay, so there's the oops, I didn't want to do that. There's the what do you call it, the BSF file, the block diagram version. And what you can do is I should be able to add what you can do is you can connect up input and output pins, and from the output pin here you should be able to just select Q25 as the only interesting output pin. Because this counter is a 26-bit counter, it's got a single clock input, and you probably can't read it, but it's got 26 bits as output. We only really want one of those bits. We only really want the Q25. And I've just, again, I should just be able to insert a pin, an IO pin, but I've forgotten. I was doing this yesterday. Okay, so we have some labs to do. I would like to try and figure out if everybody's okay with lab 5. I would like to make sure that everybody's on the right track with lab 6. And if you've approached lab 7, it would be good to see how you're going with lab 7. Let's take a break. I certainly need it. I will put up the 10-minute timer again, and we'll go with that. Thank you.
Alright, today I'm going to walk you through setting up a 1 Hz onboard clock on your DE1 board so that you can use it to blink lights or do whatever you like. So the first thing we're going to do is start up Quartus. And I'm going to go through these steps pretty quickly because I actually have a video tutorial on this site as well, so I'm just going to go ahead and... So if you want to see these steps a little slowed down or in more detail, just check out the other video. That's what I need right here. Should remember that, but it doesn't. Okay, now Quartus has a few mega functions that you can use, and we're going to use one of those there to let you design your own counter and have any inputs or outputs you whatever 2 to the 20. Now, I'm not sure what that is. I'm going to hit yes. Now, this is our LPM counter, and you'll see that there's quite a few less options than when it first came up because we're not really using any of those fancy things. All we want to do is divide by 50 million. So we're going to need an input, and oops, there we go. Less options than when it first came up because we're not really using any of those fancy things. All we want to do is divide by 50 million. So we're going to need an input, and
Okay, let's see if we can actually do something useful today. So looks like I don't have Pol Pot. So we've got a couple of labs outstanding. Right, the main one the first one is the group one with lab 5, right, to deploy the, I think it was lab 3, the half adder, to the FPGA board. Has anybody got any issues with that we should have a look at? So the remember the issue that I think we went through last week is that right, I talked about clocks this week, but the issue that we talked about last week is that the LEDs and the switches as a class, no, you got to do it as a group, Jordan. You say we cancel lab 6. Oh no, it's easy. It's easy. Right, so I'm okay to push off the due date. That's okay, but so the issue is that these, both the inputs and the outputs, were active low, right? That was a problem. Once you got it deployed to the board, it didn't work the way you might expect it to work. Okay. So I'm assuming everybody's okay with lab 5 and everybody's panicking about lab 6. So let's go to lab 6. Let's see what lab 6 is about. Wherever lab 6 got to, there it is. Right, so lab 6, the problem is, what's the problem? Glitches, right? And we've tried everything we can with our implementation, excuse me, with our implementation of the counter to remove those glitches. And even if we get rid of the glitches on the carry, which we don't actually see until the carry out, right? There's a glitch on the carry out just there. Even if we get rid of all of those, we still have a problem because we don't seem to be able to remove the glitches from all of the sum output bits. So what I did to try and get rid of it, let me just run the simulation tool, and let's see if we can see any of those glitches again. What I did to get around it is I threw out the thinking about solving the problem using discrete logic, and I just thought, well, let's just solve the problem using a VHDL approach rather than rather than a discrete logic approach. And let's finish it, all the clattering and banging that's there. Okay, and I'm just going to recompile those two. And then I'm going to simulate that one. Add all of those to the wave. And go to the wave. And then let's simulate it. Okay, eventually we get the full simulation, right? And remember, we were looking at, I think it was 1750 nanoseconds to 1850 nanoseconds. And we had, let's just open up those. We had glitches at around the 1800, and I think you can see now that there are no glitches there. Okay? And let's just scroll through and see if we can see any glitches. Right, mostly the glitches happen at those transitions, and I can't see any glitches anymore. Right, all of our outputs are nicely steady at either 0 or 1, and they transition really nicely quickly. Let's just see if we can make the range a bit bigger, go from, I don't know, 2000 nanoseconds to 4000 nanoseconds. Right, and then let's just see if we can scroll through and see if there's anything untoward happening. And I don't think there is. Okay, and then it's the end. So what did I do again? I think I can I pull that window out again? Detach window, there we go. Right, so what did I do? Well, this is our 4-bit adder, and I actually had started editing it the old version, right? I started doing look-ahead carries and all sorts of things. This is the discrete logic version with all the 4 instances of the full adder and all the connections between them. But basically I threw that out, and I just decided I was going to use the addition operation that I have access to in VHDL without having to do a discrete logic full adder. Right, and then I decided I've got an internal signal which is a 5-bit number, and I've got a couple of 0 vectors, and I just take my 2 inputs and I concatenate them with a most significant bit 0 vector. I take my subtract input, and now admittedly this isn't implementing the adder subtractor that I've asked you to implement, so you're going to have to figure out what that means. But now all I have to do in order to do the addition version is add them up using the plus operation in VHDL. I store that in a as I said, in a 5-bit vector, and then I pull out the low order 4 bits into the S output, and I pull out the most significant bit of the 5 bits into the carry out output, and I'm done. And I hope you'll agree that writing the 4-bit adder, it's not an adder subtractor, but writing the 4-bit adder like that is simpler than doing that, and then it's simpler than doing the look ahead carry version of this as well. Okay, let's just see when things are due and fix that, right? So where's the assessment calendar? Right, so Lab 5 is due today, and I'm hoping everybody has had a chance to do Lab 5 now. Lab 6 is not due for 2 weeks. Okay, so it's not due until November 7th, and then we've got Lab 7, which is a group 1, and Lab 8, which is also a group 1. Can you explain what... oh, 0, okay, sure. I can do that, Tommy. Let's go back here. So, and this is a bit confusing, right? In VHDL, the logical OR operation, we can go back to the top of the code. Yeah, top of the code has right, so there's the, in fact, why don't I do this? I will copy that, and where's the, so I've just cut and pasted all of this code into the materials chat link, Zach, so you can see everything that I'm doing. Okay. So let's get back to Tommy's question. Logical OR in VHDL uses the keyword OR, right? And logical AND in VHDL uses the keyword AND. That's different from, say, Java or C or C++ or C Sharp or most other languages, or what is different about VHDL is that there's a thing called a concatenation operator, and that in VHDL is ampersand, whereas in C versions or Java-like languages, or even maybe that ampersand means either logical and or bitwise and, right? And it's not. Here it's a concatenation operator. So what it lets you do, it lets you take 0 and 0 and generate 0, 0, right? So let's just go back and see. So at my constant 0 is just a single 0. And A in, if we go back to the top, A in is a 4-bit vector. So what this is doing is it's prepending the 4 bits of A in with a 0. And same with B in, it's prepending the 4 bits of B in with a 0. And then my subtract input is just a single bit. So in order to make the addition between these different things sensible, I have to make it also a 5-bit vector, a 5-bit number. So I've created another constant called zeros that goes from 4 down to 1, and in this case I'm just initializing it to 0. Right, that's a shorthand for doing that. Okay, so, and again I'm prepending my single bit of subtract with 4 zeros. So now I have 3 5-bit numbers, and then I'm just adding them together with the plus operation. Now, there is something that I didn't tell you that you need to notice. In order to do that plus operation, I need to include another library. I need to include the unsigned library from IEEE. Let's just let's save that. So let's just, what I'm going to do is I'm going to comment out using that library. So Tommy, did that explain what I was doing with that 0 ampersand A in? You okay with that? Okay, cool. Right, so this is the error that you would get, right? Can't determine definition of operator plus. Found 0 possible definitions. Right? So for adding 5-bit numbers together, I can't do that in standard VHDL. However, if I include the std logic unsigned library from IEEE, then it lets me compile and it will find the appropriate addition operation. So Jordan, does that give you enough information to get on with Lab 6? Remember, Lab 6 is an individual lab. Okay, so the code that I just put into the materials section, that should give you a big boost towards getting it done, but remember, it's not dealing with the subtract component, or the subtract part, so it will be it won't implement everything you need. You need to figure out how to do the act on the subtract input, negating B in, so you'll need to figure out how to do 2's complement, take the 2's complement. Okay, no worries. Yeah, it should be okay on YouTube. I should actually check that, but I think it's okay. Let me see if I can have a look at that right now. Okay, no worries. Yeah, it should be okay on YouTube. Yeah, that looks okay to me. Check that. So I shouldn't have that running in the background. It's you can hear the lag there, can't you? Okay. That's Lab 6. I haven't started Lab 7. So let's have a look at what Lab 7 is about. If I can figure out where it got to. I don't want to edit it, I'm just going to go there. So let's go there. So Lab 7, right? We've got an up-down counter, and it's got to be an 8-bit counter, and we want to and that was why I was talking about dividers, and I may change that the statement of this now that we know a little bit more about it, but let's have a look at it. Right, so we've got to implement this sort of entity. Let's see if we can't do that. So this is Lab 7. So I'm going to close that project and I'm going to do a new project. And let's call it Lab 7. And we'll put it there. Lab 7. And it's going to be an empty project. We don't have anything there. I'm going to go and select the C8 variant, which is, I think, the device we're using. Right. I'm going to not have to go in and change this later, so I'm going to select Model Sim Altera and VHDL as the implementation language. And that tells me everything I wanted to know. And now I have a Lab 7. So let's make a new VHDL file. Right, new VHDL file. And here's the code that I just got out of Blackboard. And there's my entity description. Right, we've got a, let's call this up-down counter. And let's see if that compiles. Doesn't do anything yet, but let's see that it compiles. I just want to make sure I'm not giving you a bad start to the... Now notice one thing we've got here is there's the top level entity name is probably not what we want. Right, the only entity currently in here is up-down counter. Right, so we've got to do something else. So let's do this. Yeah, let's do this. I'm going to make a new VHDL file, and this is going to be called Lab 7. In fact, let's just grab that first piece. No, didn't let me grab that first piece. Let's copy it. Let's paste it. And this is, I'm just going to call this Lab 7. And then we need to figure out what our port statement is. And let's just say that our port statement for this lab, we want a clock input. Which way around is it? Is it type and then, no, direction then type, so instead of logic. And this is supposed to be an 8-bit counter. So we will do that. We'll do it, let's just do it the same as the device, right? And let's put that in Lab 7. It's still not going to work quite properly because we need an architecture. And this time I'm going to call it Lab 7 architecture of Lab 7. And within my architecture, I was just looking up here how to define a component again, right? So within my Lab 7 architecture, I'm going to have that port statement, right? Or that component. And I need to end component. how do I use that? I do something like that and map ports. So then I do a right, I do that, and then I do a port map. Oops. And I need to map well, one way to do it would just be to map clock to clock and count to count. Let's see if that compiles. What I'm doing is I'm taking the up-down counter device, this one here, and I'm wrapping it in another device. The reason I'm doing that is because I want to be able to do something like we did with the counter, the dividing counter earlier. Is I don't want to feed this up-down counter, this 8-bit up-down counter with a I don't want to feed it with a I've got something wrong there. I don't want to feed it with a 50 megahertz clock. I want to feed it with a slower clock so I can actually output some of the bits. So what do we got? We've got a expecting port map clock to clock, port map, it should be commas. Right, I should have had a comma there rather than a semicolon. Let's just see if that compiles. So now what I can do inside the Lab 7 entity is I can take the 50 megahertz clock and I can divide it down. At the moment, I've just connected the clock coming into Lab 7 straight up with the clock going into the up-down counter. But what I want to do at some point is do that division down by 50 million or whatever it happens to be. Yasmin, are you missing audio, are you? That's no good. I think I'm unmuted. Okay, so I didn't do the right thing. I need to have a count up as well, right? So let's just do that. Let's see if we can get this to compile. It's not doing anything at the moment, but let's see what it does. Let's just kill that. Okay, so that compiled. So now we have the code that is in the lab, and we've got it wrapped inside this lab 7 entity, which is our top level entity. And for some reason, Quartus has gone into La La Land. It usually doesn't do that for me. That's still running. Oh, there we go. Let's come back. Sorry. Okay. Yes, it quit. Okay, let's try that again. I don't know what I did to it to tell it to go away. And it's forgotten everything. That's no good. I think I want QPF files. There we go. That's interesting. Huh. It went and decided to change the top level entity for some reason. I'm going to change the top level entity back to lab 7. Right, so there's lab 7. And as I said, at the moment it doesn't do anything different. It just puts a shell around my my up-down counter. And it's just, there's the up-down counter. Okay? So let's think about what we want to do in the actual up-down counter. Right, what we want to do probably is, well, we probably need a signal, right? And let's call our signal count, and it's probably going to be a std logic vector 7 down to 0. Or maybe we make it an integer, right? And then what we can do is we can have a counting process that takes in the clock, every time there's a clock, we can say if clock event, and so on a positive going transition, right? So clock equals 1, then we can do something. And what we can do is we can say count equals count plus 1. Now the trouble is we only want an 8-bit counter, right? So 8 bits, the maximum value you really want is 255. So if count equals 256, then count gets reset to 0. Right, so now we have a modulo 256 counter. It goes from 0 up to 255, back to 0 again. Now the other thing we want to do is we want to connect, in fact we want to connect up, well, we want to do two things. One thing is we don't want the signal to have the same name. So let's just call the counter, right? And then for our output, that's what we'd like to do. Can anybody see a problem with that? Jacob, can you see a problem with that? With that line 25 that I just put on the screen? Let's see if it compiles. No, it's got some errors. Funnily enough, counter. There we go. So that's the problem, right? Remember that VHDL is what I would call a strongly typed language. So that means that when you go from one type to another, you can't just do an assignment. You've got to do something special. Okay, so let's think about how we do the conversions, right? I think you remember that there's a way to convert from one type to the other. if you used unsigned addition, would it not disregard overflows, so it would be 0 when you add 1 to 255? That is true if my counter variable, let me just make it visible, right? If my counter variable was defined as an 8-bit number, yes, that would be true. My counter is defined as an integer, which I believe by default in VHDL is a 32-bit number, right? So you could, the count is just the output, and I can't do anything to a VHDL output except output it, right? I can only assign a value to it. I can't add 1 to it, for example. If I tried to do count equals count plus 1, VHDL wouldn't compile. I need to do the addition or manipulation on an internal signal, and then I just assign the value of that internal signal to the outputs. Okay, so the question I was asking Jacob was that assignment on line 25, I think it was. Yeah, so that assignment isn't going to work. So what do I need? What I need to do is do a conversion here. And I think, so I need to go from an integer to a std logic vector. And I think I can do that. Now, I thought it was something else. I thought you could give it a parameter. Sorry, I'm just looking up something. So we want to go from integer to std logic vector. Right, so what we might want to do here is something more like that, and then that, and we want to make it 8-bit. Now, I'm not sure I've got the right libraries in here. I think I need to also include, I think it's called numeric std unsigned. Is that right? No, it's just numeric std. Okay, let's see if that gets around our type conversion issue and doesn't cause any other problems. Okay, it's compiling. And so I believe that might do the right thing. So let's just see about, once it's finished compiling, let's see about simulating it. Right, we don't want to, with these things, we don't want to go straight to the board. We want to do a simulation first. And actually, I haven't set up a test bench. So let's do that next. So was it processing, start, test bench writer, right? And we've got the lab7.vht file. But I need to make sure that I add that so that it compiles. Let's just look for all files, and there should be a lab7.vht file there. Okay, so I did that. The other thing I need to, oops, I didn't want to go there. I want to go here again. And I want to go to simulation, and I need to set up, remember I need to set up the test bench. So I'm going to go here to the test bench. I'm going to create a new Lab 7 test bench. And I don't remember the name of the top level thing in here. So there's the VHT file added. I may have to come back here and change that name. Let's just go back in here and let's see if we can open up that VHT file and get the name of the entity that it created. It's probably got a TST in the name. There we go. Lab 07 VHD TST. So let's go back to our settings, simulation, test benches, edit that one, and the top level module is that one. Okay, now we recompile, and I still have a problem in that my test bench actually doesn't do anything yet, right? So how do I get my test bench to do something? I've got to do something with the clock. It's already defined a clock signal. Let's just wait for the compilation. But what I'm going to do is I'm going to initialize the clock signal to that, to 0. And then what I'm going to do is within my process, I'm just going to say wait for, let's say 10 nanoseconds, and then say clock is not clock, and I'm just going to do that a few times. So I can get a sense that my clock is actually clocking. Now let's recompile that. So what I'm doing, let's just think about what I'm doing with Lab 7. So this is for Lab 7. And what I'm doing is, one, I'm creating a VHDL up-down counter. Right? And then I'm wrapping the counter inside another another entity. And the reason I'm doing that is so that I can divide the clock. Slow down the clock. Right? I could have done that clock division inside this first one, but I prefer pulling apart the functionality and implementing one part of the functionality, the up-down counter, just in the up-down counter, and putting the other part of the functionality into the wrapper. Okay? And then what I did is I created a test bench because I want to simulate the counter before I deploy it to the board. And so that I can simulate it. And then here we go. The fourth piece is then I want to deploy it to the board. Right, so what's happening in these first two steps is I have my outside device, which is my Lab 07 device, and within that Lab 07 I have an instance of the up-down counter. Right? And inside this Lab 07 I'm doing the divider. Well, I haven't done it yet, but I intend to do the clock division. No, maybe I have. I think I just wrote it, didn't I? Maybe a better way to do it would have been the following. Right? Maybe a better way to do it is to have this Lab 07 outside device have the up-down counter but maybe it would have been better to use that a separate dividing entity, and then the only thing I need to do in Lab 7 is to connect them up, right? Even better, and I haven't given you enough information to be able to do it yet, because I wasn't as well prepared for today as I should have been. An even better way to do it would possibly have been to, like I said, do the divider, but then rather than writing our own up-down counter, understand how the library LPM counter works and use that instead, right? And in fact, in order to do this piece here, I could also use the LPM counter, the library version. Okay, so there's a few ways to do this. Okay, so that all compiled, and let's see if we can run the simulation tool. Oh, I've already got it running, so let's not do that. So we've got lab 7. Oh, it didn't compile the test bench. Let's just, I thought I just compiled the test bench as well. Let's just check to see it found VHT. Ooh, it didn't find VHT. Okay, so I'm going to have to redo it again. Oh, I can't. Do. I missed out a keyword. For some reason, it didn't bar, so I need to say wait for, I think. Okay. Let's do that. And let's see if that compiles. And let's check to see that it is actually compiling the test bench as well. We'll just put that filter on the output of the compilation. No? That's all right. Let's just check. It says to compile the test bench. Test bench name is lab 7. The file name is lab7.vht. For some reason, it should be. Let's just see if I can see it. It's pulled it out now. Let's just leave it alone until it finishes chopping and changing what it's doing. Okay, might be alright now. So let's have a look under the work. Okay, so now we've got everything that we expect. Alright, we've got the lab 7 outer shell, we've got the up-down counter inner shell, and we've got our test bench. So let's simulate our test bench. and we will add that to our wave. And let's see what happens. I suspect we've missed out a few things that we need to... Oh, that wasn't too bad. So something looks like it's happening there. Let's just, what's that, 100 and few nanoseconds? So let's just do a range of 0 to, let's say, 200 nanoseconds. Okay, so there's our clock. That's doing the right thing. And our... looks like our bits are also doing the right thing, right? So the... for every clock cycle, the least significant bit is changing, is toggling, and then for every 2 clock cycles, the next most significant bit is changing, and then we don't do enough clock cycles to see whether the bit 2 is changing. And we haven't set up the count up to the count up signal to do the right thing. But it looks like it's starting to do the right thing. Let's see if we can make it a little bit more. Right, and this is an 8-bit counter, so I could go through and do all of those things lots of times, 256 times maybe, but let's make it a bit more sensible, right? And let's have a right, let's have a variable definition. And let's call it right, let's call it increment. And what we'll do is we'll say for increment. Now I've forgotten the loop syntax, which is bad of me. So let's just go and get the for loop. Right, so for increment in 0 to 511 loop, and then we can loop that, right? So 512 times, and then we can end the loop. And let's see if that compiles. We probably don't need to compile it there. I can probably just do the compilation over here on my simulator. Let's recompile first. That looked okay. And then we can simulate our test bench again. Okay, we're simulating. We'll add that to the wave. And go to the wave. And run that for a bit. And maybe run it for a bit more. Okay, so that looks like it's doing the right thing. And again, our up-down counter is not there, but now you can see that for every time we go up a bit, the period of the change in the bit's value doubles, right? So the change in the least significant bit is double the period of the clock. The bit 1 is double that, bit 2 is double that, bit 3 is double that, bit 4 is double that. So it does look like now we have an 8-bit counter, and it's counting. One thing I'm a little concerned about is it stops, right? And maybe our clock needs to go for a bit longer. Not quite sure why that would be. Right, our clock, our simulation we probably need to keep it going. We probably need to this is only 256. We need actually to make it go to if I want to see whether the clock loops back to 0 and keeps going, I need to make the number of toggles 1024 rather than the number of toggles being 512. If the number of toggles is 512, I only get 256 full clock cycles, right? Because a cycle has 2 toggles in it, one up and one down. So let's see if we can see the counter keep going. So I don't think I need to recompile the whole thing. I think I can just recompile the simulation and then restart the simulation. And add those to the wave. And then simulate it. Right, and now it's gone for a bit longer. And let's see if we can see what's happening. Okay, and now we can see that in fact it is going back to 0. Let's just zoom in on around the 5110. So let's go from say 4900 to 5500. Okay, so there's our clock, and there's our all ones on the output, and then the next clock cycle it goes back to all zeros. All ones, all zeros. So that's our transition time, or our wraparound time. Okay, I could deploy this now to the board, right? Let's just see what the pin planner would allow us to do. Right, I have an input. I have 2 inputs. I have the count up and I have the input here. My count up isn't connected to anything in my implementation yet, so it's not going to do anything. I'm just going to use pin 23 as my clock, and that's going to be way too quick. Let me just remember what the what LED 1 is. I keep forgetting LED 1 is pin 87. So I'm just going to connect up the most significant bit, which is going to be the one that changes most slowly, to that LED. Okay, so there's my pin planner done. Now I need to recompile, because every time you change the pin planner on the pin assignments in the pin planner, you need to recompile in order for the appropriate connections to be generated. So let's see what happens there. Okay, that's looking like it's doing the right thing. And let's see if we can program the device. Ooh. For some reason, it's not going to let me program, and I'm wondering whether it's because I don't have all of these connections connected up. Ooh. No, it's because it says there's no hardware for some reason. There we go. That's better. I don't know why it changed that setting. So this is kind of interesting. Let me see if I can pull that up. Right, I've don't know if I can get that into focus. You can see all of the LEDs there have lit up, right? Even though I've only connected up one of them. So let's go back and see what that might mean. I think it's because, actually I'm not at all sure why that would be. Okay. Rather than watch me doing a lab, why don't you spend some time now trying to get either lab 6 done or lab 7, and I'll answer any questions that come along. That sound okay? And feel free to join the queue. I'll take whoever asks a question first. Everybody's gone to sleep. No?
I was muted. Could you show the up and down counter VHD and the Lab 7? I think I'm missing a few lines.
The up-down counter VHD, let me just pull that out as a separate window so you can see it a bit better. Okay.
Yes, line 26 there. Hold on.
Yeah, so in order to do that one, you also need the conversion routines, which are in numeric stood at part of the IEEE. Okay, does that help?
Yeah, and Lab 7, or yeah, the Lab 7 VHD. I think I'm missing where
Labs.
you added the component.
Yeah, let me pull that one out as well. Okay, so the test bench, the only code that I've changed in the test bench is there, right? The test bench template writer should have generated everything else for it. Actually, I also added the variable there, but everything. So that apart from the begin, everything else there is stuff I wrote. Nothing else above there was stuff I wrote. It should have been generated by the template writer.
All right, and how about the VHD for Lab 7 as well?
The VHD for Lab 7. We can have a look at that. Is that it there? That's it there. So let's detach that window as well. Right, so here...
Yeah, it's line 21 there.
Yeah, so that is instantiating a version of the up-down counter, right? We define the component that we're looking for here, and to actually instantiate it, we need to do that port map statement. Tommy's asking if the test... Is that okay, Quinton? Is that enough?
Yes, perfect, thank you.
You're welcome. So Tommy's asking if... Do we have a... test bench in Lab 6. Where's Lab 6? Yeah, so so in some ways that test bench is not, there's no asserts or anything like that there, right? So it's not really acting as a test bench. What we have to do is it's just running the simulation, and we're then eyeballing the simulation to check for glitches. And I couldn't figure out how to get the test bench to fail on those glitches, right? So yes, the test bench is perfectly adequate for this. The only thing that you'll have to do though is compare this glitched version with hopefully an unglitched version of your Lab 6. And particularly the first glitch in the original, in the glitchy version, was happening at about 1800 nanoseconds in the simulation, and that was pretty consistent. Right, I don't think I captured it there, but so the aim is to take the original, show that there was a glitch, say at 1800 nanoseconds, and maybe there's a few around there, right? This particular snapshot shows several glitches. There's some here, there's some here, there's some here, and the aim is then to compare those times with the original to the unglitched version that hopefully you've made, and just so you can demonstrate by example. It's not really a test bench in that I haven't figured out how to assert to find those glitches, but that should let you do the assignment. Does that answer the question, Tommy? Okay. Okay. Any other questions about lab 5, 6, or 7? Are we able to use if logic in the process statement to do the subtraction? That is the million-dollar question. Let's just go back here. I'm going to close that project, and let's go see if we can find where I put the other one.
Sorry, my mic wasn't working. Yeah, I was just confused if like we can just like say if subtract is 1, do something, or if not, do something else.
Yeah.
Oh, okay, so we can just do that. Okay.
That
I just wanted to know if that was possible.
That's so. Part of the reason I've had you strain your brains on the lab is because I want you to start breaking away from the 363 approach to logic design and start thinking more VHDL, right? And exactly what you just said is the way to do the subtraction. Instead of, I think, instead of using the plus sign, you might put a minus sign in front of the B component, right? Because I think it was the B input that was being subtracted. You may then also have to play with whether the subtract bit comes in or not. But yeah, that is a perfectly acceptable way to do it. Okay?
All right, thank you.
You're welcome. Right, so what Tommy is suggesting is instead of this is right, there's no process statement here. It's all just direct hardwired connections. So what Tommy is suggesting is what do we want to do? We probably want to do A in, B in, and subtract, right? And then begin, and then end process, do work. We probably want to do something like, we don't need to I don't think we need to play around with the subtract then, right? Because what we can do is we can just say if subtract equals 0, then we add, and we don't have to do anything special. Otherwise, right, we can do something else.
Now, do you want this to be consistent with Lab 4, where like where the carry flag would be high, or do you want it to do like real subtraction?
You probably want it to be consistent with the other lab, right? So
Okay.
that's going to make it a little bit more complicated than just what I did there. But you do want it to be consistent with the other lab. Okay? Let's see if that actually compiles. Right, and that's one of the beauties. I apologise, my dog has gone ballistic over something. That's one of the beauties of this is of VHDL, is that you can do things at a more abstract level or a higher level, rather than necessarily connecting up wires. You can still connect up wires, but just being able to do addition and subtraction, for example, is much nicer than having to figure out how to do addition and subtraction in binary and then implementing it in discrete logic. Well, it compiled. Any other questions? If you don't mind, I've just had some bad news, and so I'd rather end the lecture a little early, if that's all right. Okay. Let's leave it there. Thank you very much for your time. Feel free to ping me if you have any questions via Discord or via email. Happy to do it. And I'm just going to shut down the